Apart from sunlight, the Earth is essentially a closed system. The rate of population growth at the moment of around 1.1% is still very high in historical terms. The shortest estimate of human history comes from a young Earth assessment of biblical chronology, 6,000 years. It's a starting point because it will produce the largest possible average population growth rate for human history. That average growth rate is 0.36%. Choose 100,000 years and the average is 0.02%. There are very good reasons why these average rates are so low and why the present rate can be judged as unsustainably high by a long shot. Since humans are predominantly made of water, it can be safely assumed that the volume of water contained in people on Earth can never exceed the total volume of water that there is on Earth. This amount is fixed and for all intents and purposes won't change. For this particular scenario, the number of doubling periods is 32. What would happen if present population growth rate continued unchanged? At a population growth rate of 1.1%, within roughly 2,000 years, there would be more water in humans than water in the world. This isn't going to happen. There's one inescapable conclusion of all this. Human population growth will effectively cease, and in a time frame that is of relevance. Having established that human population growth will cease, if for no other reason than finite water resources, what about energy consumption? Mankind is always finding new and previously undreamt of ways of consuming energy. This is important to keep in mind when various growth rate scenarios are extrapolated into the future. When considering questions of energy sources, it's important to get right back to the primary source that occurs naturally. There are 5 basic forms of primary energy that are of relevance. 3 renewable and 2 non-renewable. They are solar energy, geothermal energy, tidal energy, fossil fuels and nuclear fuels. Solar energy. Every year the disk of the Earth intersects the same amount of energy flowing from the Sun. This figure is easily calculated and it's not really open to conjecture. Wind energy, hydropower, wave energy and biofuels are all derivatives of solar energy. The total amount of energy of all types marketed in the world in 2004 is quoted in International Energy Outlook 2007 as 447 quadrillion BTU. The energy density of sunlight falling on solar panels of Earth-orbiting satellites is around 1,300 watts per square metre. From this figure and the diameter of the Earth, the total kilowatt hours of solar energy intersected by the Earth each year can be calculated. From there, the kilowatt hours can be converted into BTU or vice versa, and the two figures divided. The outcome of this calculation is that the amount of energy from the Sun that is intersected by the Earth is 11,514 times the amount of energy marketed in the world in 2004. This appears to be a large number, but how many doubling periods does it equal? The answer is less than 14 doubling periods. What if one conducts the hypothetical thought experiment that society moved over to only using energy derived from solar power and derivatives of solar energy, such as wind power? While any prediction of timing is purely hypothetical, the maximum upper limit of the number of doubling periods for such a scenario is not hypothetical. There is no upside uncertainty. If energy consumption growth over a long period of time were to average just 0.5%, the limit would be reached in less than 1,960 years, or 980 years at 1%, or 490 years at the presently forecast 2%. If, as a result of widespread belief that this energy was boundless, clean and environmentally friendly, consumption grew to 4%, the limit would be reached in less than 245 years. At present typical rates of global energy consumption growth, not even literally all the solar energy in the world will be sufficient to meet requirements in 500 years' time. Apart from solar energy and its derivatives, there's only 2 other sources of renewable energy on Earth, geothermal and tidal related. Both of these are a tiny fraction of the energy intersected by the Earth from the Sun. Adding them into the above consideration makes no material difference to the outcome. Estimates of the total energy flowing continuously from the interior of the Earth vary in a range of around 5 to 60 terawatts. How much could conceivably be converted into electricity will be some tiny fraction of that total. Even if it was all recoverable, freezing the Earth from the inside might not be a good idea. Whichever way it's analysed, geothermal energy is far from being a vast resource when compared with total global energy consumption, even right now. At the lower end of the estimates, the world is already using several times the total theoretically possible geothermal energy available. even at the most wildly optimistic projections of what proportion of total geothermal energy could be extracted, the higher limits would still not be sufficient. Even if the upper estimates are wrong by some large amount, exponential growth will not take long to overtake such upward revisions. The last form of renewable energy is tidal power. Since this is a smaller fraction again compared with geothermal energy, it's not necessary to do any analysis to conclude that tidal power will be of little help when it comes to dealing with global energy demand. Fossil fuels. Most famous among the forecasters of fossil fuel production is M. King Hubbert. In a paper published in 1949, Hubbert noted that the age of oil would, on the scale of recorded human history, be rather brief. Now, there's been so much discussion of peak oil in the media that I'm not going to elaborate further on the subject of peak oil here. But moving on from peak oil, of all fossil fuels, coal is most abundant. Realistic projections for coal, by those whose job it is to make such projections, involve much shorter timeframes than those discussed here for solar energy. For example, on page 51 of International Energy Outlook 2006, worldwide recoverable reserves of coal were quoted as being enough to last approximately 180 years at current consumption levels. There's a reference footnote at the bottom which states the following, quote, based on IEO 2006 reference case forecast for coal consumption and assuming that world coal consumption would continue to increase at a rate of 2.0% per year after 2030, current estimated recoverable world coal reserves would last about 70 years, end quote. Multiplying the resource estimate 2, 3 or even 4 times will, on the scale of human history, make little difference to the overall outcome. All of this might seem a powerful argument for nuclear power, but it's not. Nuclear power is a non-renewable energy source. As was demonstrated earlier, even seemingly vast non-renewable energy sources are no match for society's appetite for exponential consumption growth. To make matters worse, whether it's coal, gas, nuclear fission power or even nuclear fusion power, all these non-renewable energy sources produce harmful waste. The amount of waste produced is a function of how much electrical energy is produced. More energy equals more waste. If electricity consumption continued to grow at 2% for the next 1,000 years, what multiple of non-renewable energy resource would be required to meet those cumulative requirements? The answer is over 24 billion times. There's various figures quoted for the amount of uranium and thorium reserves in the world as a multiple of present annual electricity requirements. None are in the order of 24 billion. The world might just scrape through 1,000 years at 1% per annum growth rate before the resources are totally exhausted. Even give or take a very large error in these estimates, one thing is certain. At typical consumption growth rates, uranium and thorium cannot see society further than a fraction of recorded human history. Inevitably, all this leads us to the question of fusion power. All I will say about fusion power is that 40 years ago, fusion power was considered to be achievable within 40 years. 40 years later, fusion power is still regarded as being 40 years away. It can be concluded that whichever way the problem is cut, getting past the next 1,000 years with exponential energy consumption growth is difficult to arrange from a resource supply point of view, let alone from a waste management perspective. None of the options, fossil fuels, renewable energy or nuclear power, will sustain growth of any significance. There's only one inescapable conclusion that can be drawn. Growth in the rate of energy consumption will stop. For all practical purposes, everything tangible consumed in modern society requires the consumption of energy somewhere. If growth in human population will stop and growth in energy consumption will stop, by extension, one can readily appreciate the growth of consumption of everything tangible in society will stop. This will be true no matter how ingenious mankind may be. A useful analogy to demonstrate the inevitability of a halting of growth is the Petri dish. To understand where the world is heading with a continuous growth paradigm, one only needs to understand what happens to the bacteria in the Petri dish. For a while, the bacteria are happily multiplying, consuming food and generating waste in the process. The culture is growing, and at an astounding rate, a fast-forward version of society. But the party doesn't last. Eventually, the resources start to run out, and waste products build up to toxic levels. The bacteria may or may not then proceed to die completely, but with absolute certainty, it will stop growing.